All right, we'll go ahead and get started. Um, let's see, we were working on beams. So we've been talking about beams first in the context of frames and machines. And that was what separated frames and machines from trusses, is that we had to treat at least some, if not all, of the members in a frame differently than we treated them in a truss where everything was a two-force member. So beams can flex. They don't just stretch out or compress. They can bend. And so that's what we've been working on. We were working on the equation, the flexural stress equation. So sigma, it looks like a axial stress, but it's actually a little bit different. So sigma equals negative m times y over I. That was maybe 2 lectures ago, where we went through using that equation. And now we're at the point where we've done a couple of things calculating. Let's go through and look at some of the stuff we've done. Let's see. Here we were actually, this was setting up a problem that somebody asked about. That's a frame we were setting up. But here's what we've done. So we had a beam like this one, and in this particular one, we developed equations. First in section AB, then in section BC, and then finally in section CD. And we ended up with, in this case, 6 equations, 2 for AB, 2 for the next section, 2 for the last section. One of those equations in each section was an equation for the shear force, and the other was an equation for the bending moment, the internal bending moment in the beam. And so that at least sped up our process a little bit if our goal was to look at a beam and figure out where is the maximum flexural stress in this beam. That might be our question. So that's not bad. It does help us, but we probably want a little bit faster method. So what we're going to do now is take this same idea, particularly this idea of these equations in every section. We're going to generalize the equations, and then we're going to develop a series of, like an algorithm, if-then statements, to draw a picture of the shear force and the internal bending moment anywhere in a beam. So that's our goal today. These are called shear and bending diagrams. So let's start with just a generic setup so that we can take account for all of the different things we might have to deal with on a beam. So here's our beam, side view of our beam, and we'll make it a simply supported beam. So it's going to have a pin somewhere, and it's going to have a roller somewhere, and we'll put those, on the ground. And then let's go to the very center. I don't know if I drew this. Let's just say this is the center right here, and let's put our 3 main types of loads on here. So we have point loads, we have distributed loads, and we have concentrated moments. I don't think we've done a beam equation or beam calculation that has a concentrated external moment. We've done the concentrated internal moments. That's what we've been solving for. But I don't think we've done an external one, so that'll be a new thing for us. All right. One thing about these, I'm going to draw them in our positive direction. That's just so I have some signs work out later on that make things a little bit simpler. So here will be positive X. This will be positive Y. And I'm going to draw the forces in my positive Y direction. I guess I should write Y on there. So, and I'm going to put them all at the center point here. Not just so that things can be nice and centered. It doesn't actually matter. So here is our point load. I'll call that one P for point load. I will put I'll put a distributed load across the center here too. Let's start it over here. Can't get it to draw a straight line. Now this distributed load could be any particular shape, but I'm just going to draw this one as a evenly distributed load, so it's all little even across the top, but it could be any shape. I'll call that one W because it's like a weight on the beam, something like that. And then I'll put a concentrated moment and I'm going to draw it clockwise, and I'll call that C. All right. Now, these are not your normal loading setups. Normally you have them all spread out over the beam. They're not all at one single point. But we're doing this so that we can come in here and create a little section, like a little tiny section here of the beam. So I'm going to take that little tiny section, enlarge it, and use it to develop our equations that are, well, our if-then statements. So we'll try and line it up there. This is our enlarged version of that tiny little section that we just drew. So we've already done, we probably did over here, we've already decided the sign convention for internal shear and bending. I think this one shows both sides, where we've already decided which way is positive. So I'm going to use this same convention on our little section we're drawing here. So if I am on the right hand side of the beam over here, then I draw the shear force going down as positive and the bending moment going counterclockwise as positive. I'm going to say this is the moment on the right hand side and the shear force on the right hand side. Actually, I'm going to make me some room there. And then I'll have the corresponding shear force on the left hand side, which may not be equal to the shear force on the right hand side. So it could be a different number. And I'll have the bending moment on the left hand side. And I'm using the sign convention that I've already established, you know, like here. Same thing. This one looks backwards, but, you know, it's the right hand, the cut side on the right hand side of your free body diagram has the shear going down and moment counterclockwise. The cut side on the left hand side of your free body diagram has the shear going up and moment clockwise. Those are our positive sign conventions for these internal shear and bending moment. Okay, I also have a point load. I will put that here. I also have a concentrated moment, which I'll put kind of at the center here. And I have that distributed load. Again, the distributed load could be any random shape. It doesn't have to be nice and evenly distributed, but I guess my ML is going to overlap, isn't it? Let's move that over. I'll put it kind of like that. And again, I'm drawing them going upwards because I want some positive signs in these equations, but it doesn't matter. Okay. Let's see. Also, I have a width here. And I'm just going to call that, since I'm trying to do something kind of generic, and I want it to develop an equation or a set of if-then statements at an individual, like, single point, I'm going to call this delta x. Okay. Okay, I think that's most of what I'm going to move it down. It looks like it's overlapping a little bit here, or close to overlapping, so I'm going to move it down just a little, just to get it away from that other stuff. Okay. The other thing I'm going to do is I'm going to take VR and MR, so the shear and bending on the right hand side of the beam. I'm going to take those and I'm going to trickily redefine them, if that's a word. And I'm going to say that, well, the shear force on the right hand side of my diagram here is equal to the shear force on the left hand side plus whatever kind of change in shear there is between the left hand and the right hand side. So that's all I'm going to do. So this is change in shear. And I'm going to do the same thing for the bending moment. The one on the right hand side is equal to the one on the left-hand side plus whatever change happens between left and right. Okay? And you'll see why we do that in a minute. Okay. I think it's time to start writing our equation. So the easier one, and the first one when you're drawing one of these shear and bending diagrams, I think I showed you one last time. Let me see if I can find a picture of one so you know what we're after. So yeah, like this. This is kind of the picture we're after. Well, gotta scroll down to where it's at. Alright, so there's the whole thing. We want a free body diagram of our beam, and then right below that we want a diagram that shows us the shear force anywhere in the beam, and below that we want a diagram that shows us the bending moment, the internal bending moment anywhere in the beam. That's what we want to generate. Okay, so let's go back to our setup here. Alright, so the first one right under our free body diagram would be the shear. And so to calculate the shear forces, I need to do summation of forces in the y direction, because that's the direction that I've shown these internal shear forces. So I'm going to take my generic free body diagram of a beam that has all the loads that I might have on there, recognizing that the distributed load could be some other shape than evenly distributed. In fact, I might just write a little note. Let's see, let's write it in distributed load does not have to be evenly distributed. Okay, it doesn't have to be evenly distributed. It's just that that's what I drew. Okay, so let's take and add all the forces in the y direction. So we still know for any little piece of the beam, unless that piece of the beam that I've drawn the free body diagram of, so in this case this little section in the middle, unless that piece is exploding away from the beam, which is what I don't want to happen, then it has to be in equilibrium in the y and the x and then moment, all these different directions. It has to be in equilibrium. So if it's not in equilibrium, the summation of forces does not equal 0, then it's moving around somewhere, which is not what I want. And I don't really mean that it's deflecting. I mean that it's like separating from the rest of the beam. All right. So first of all, the curved arrows. So just as a reminder, the curved arrows like this guy and all of the curved ones, those are concentrated moments. Okay, it's kind of under the picture here. There we go. Concentrated moment. So any one of those that's curved is a concentrated moment, and what that means is does not have a direction like X or Y or Z. So in the Y equation that I'm writing now, none of those go into the equation. They don't operate in X, Y, or Z directions. Okay. So the other arrows, the straight ones, even if they're shear or like the point load or the distributed load, they do operate in the Y direction. Or they, in the way I've drawn them, they operate in the Y direction. So I'm assuming Y is positive when it goes upwards. So I'll redraw my coordinate system here just at the center. So VL is positive. P is positive. There's why I wanted the to draw them all in the positive direction, is so that they would be positive in this equation. W is a distributed load, but if I take W times the width, which I call delta X, then that would be the lumped version of the distributed load, whatever it ends up being. Okay, W could be a function. It doesn't have to be just a straight line. It could be whatever shape. If I calculate basically the area under the distributed load curve, then that's the lumped version of it, whatever it ends up being. Okay, P is going, oh, I already added P. VR, so it's going down. So minus, and I renamed VR as VL plus delta V. So here you can kind of see I've got positive VL and minus VL, so those just subtract each other. And my equation ends up being 0 equals P plus W times delta X minus delta V. So I don't like the minus delta V. I'm going to move it to the other side, and my final equation will say delta V equals P plus W times delta X. Okay? And we're going to use that equation to set up our statements, our algorithm. Had a little network problem there. If then. So, if, for instance, let's see, if P and W are both 0, that's an easy one. So in other words, there's no point load and there's no distributed load. So if that's true, then my equation would say, well, delta V equals 0 plus 0 times delta X. It would say delta V equals 0. And we have to remember delta V is not shear, it's the change in shear. So what it doesn't mean that the shear force is equal to 0. It just means there's no change in the shear force in whatever section where P and W are both 0. And remember, in our little picture that we were looking at, you can see that. So the first section, I can't draw on here, but the first section here is just flat. It says that there's 12 kilonewtons of shear, and it doesn't change. There's no change in the shear force from this yellow arrow to this green arrow. And then from the green one to the next green one, there's also no change. It's a different value than it was in the first little segment there, 12 to -3, but there's no change in the shear between those two arrows because there's no point load between them and there's no distributed load between them. So that's kind of what this rule is saying. So what if P does not equal 0? If P does not equal 0, so then here I'm going to say that, well, P is representing a point load, so it exists at a single little point somewhere. So I'm going to try and get closer and closer to that point, which in the context of my diagram here means sending delta X to 0, basically. So as delta X goes to 0, then the equation would say that, well, if I send delta X to 0, then delta V equals P plus essentially 0. So delta V equals P. So now there is a change in shear, and it's equal to the magnitude of the point load. We can see that in our diagram we were looking at. So here I've got a negative, because it's pointing down. In my equations, I've drawn the point load pointing up so that I don't have that negative sign, but here pointing down, so a -15. I was at 12 minus 15, I go straight down, so there's like a step change. I should put that word in there, step change, down to 12 minus 15, which is negative 3. So let's actually change this to say there's a step change. So it instantly happens. It either goes up if your point load is pointing up like mine are, or it goes down if the point loads are pointing down. Okay. Now, so if, oh, I didn't have to write the P, the if there. I already wrote if. So let's move that. There we go. That's not important. It was just bugging me. All right, so what if W is not 0? And we will say that P is 0. Because if P is not 0, then it's going to dominate that little single point. But let's say that there's a space where P, there's no point load, but there is a distributed load. That's what we're talking about here. That doesn't happen on the one we've been looking at. This one doesn't have distributed loads. Let's see if we can find one that might have some distributed loads on it. Here's one. Look at this one for a while. Where is it at? There it is. So you can kind of see this little section right here, just to the left of the 100 Newton point load. There is a piece of a distributed load. Then you have the point load, and then there's another piece of the distributed load. So in the shear diagram, you can kind of see it's not 0. There's no change, and I mean there is a change, but it's not like a step change. It gradually changes. And so that's what's going to happen under a distributed load, is there's going to be a gradual change in the shear force, either down or upwards, depending on if your distributed loads are pointing down or upwards. Most of the time they're going to point down. So let's write out our equation. So if W does not equal 0, but P does. So now the distributed loads are not at a single point. So I don't want to send delta X equal to 0. So I don't want to like look at a single point, but P is 0. So I end up with delta V equals P is 0. So W times delta X. And again, W could be a function of X. It doesn't have to be just a single number like we've been doing. It could just be, any kind of equation in there. So what I could do here is I could just rearrange this thing and say delta V over delta X equals W. So if you look at that, then delta V over delta X is kind of like delta Y over delta X, or dy over dx, which is a slope, right? So this guy is slope, and since I'm delta V, or dv over dx, delta V over delta X, then it's the slope of the shear diagram. And it's saying that, well, the slope is equal to whatever that W thing is. Now for us in this course, W's, when we're doing shear and bending diagrams, we're only going to do evenly distributed loads, because you're doing these by hand, and if the distributed load is, even if it's like a triangle, then it gets a little more complicated to do by hand. So for us, in the context of the course, they're only going to be evenly distributed, like I drew up here, like this. And like the one we're looking at here, that's an evenly distributed load, or distributed load, yes. But they could be any shape you could imagine. And so it says that the slope of the shear diagram equals whatever that thing is. In fact, on their example here, you can kind of see their slope is 1 over 10, and their well, I guess that's 10 over 1, rise over run, right? 10 over 1. And you can see that their distributed load value is 10 newtons per meter. So the slope of that line is going to be directly related to the magnitude, it's not really a magnitude, but the value of the distributed load. And so you can kind of see it slopes. And for every meter, so this one is 10 meters long, every meter it goes down another 10 newtons. So this one started at 200, so there you can kind of see the The reaction at the end is 200. It's a point load. Point loads have step changes up to 200. There's nothing happening between the 200 and where the distributed load starts. So there's nothing happening in the shear. It's just staying. It's not going to zero. It's just staying at 200. And then you get to the distributed load. Couldn't think of the word. And it is pointing downwards. So I'm losing value on my shear. It's going to a smaller number. And I started at 200. And then every meter I lose another 10. So 200, I go for 10 meters, I lose a total of 100 newtons. So you can kind of see it starts at 200 and it goes down to 100. Don't worry about these numbers inside the shaded area yet, that's for later. So we're looking at this 200 is the height of the shear, and it goes down, 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 down to 100. So the total change over that distributed load is equal to W times X, however far it is that distributed load is existing. Okay. Oh, you're welcome. So thank you in the chat. All right, so that's it for the rules for the shear force. We don't have to do anything with these curved arrows. They are only affecting the internal bending moment. But now we need to do that. So why don't we take our entire diagram here and we'll copy it, and we'll go down here and we'll write us a similar set of stuff, but for the internal bending moments. You don't ever have to, as far as the class goes anyway, you don't ever have to recreate this thing. And you don't even have to rewrite these rules at any point. You just have to know how to use them. So it's not like these are the important thing to remember. It's just the concept of it. All right. So here we're going to do the same thing, except previously we wrote the summation of forces in the y direction. Now we're going to write summation of moments, and we're going to write moments about this center point. I'll call it A. So that's center point A. We're going to write summation of moments about that point. I will say clockwise moments are going to be positive in this equation. All right. So let's just get started with the shear force, VL. Now its moment arm is only half of delta X, so that's what we'll put, delta X over 2. Here I get to choose, do I want VL plus delta V as VR? In this case, I'm not interested in delta V anymore. I'm going to do VR. Same thing, it has a delta X over 2 moment arm. You could get to the same result that I'm going to get to if you plugged in VL plus delta V for the magnitude of VR. That's fine. These both go clockwise, so they actually are both positive, so that's important to know. I've got that concentrated external moment, C, and I've drawn it clockwise. I said that clockwise is positive, so it just goes in as plus C. So that's important. We haven't done a lot of concentrated moments, but no matter where the moment is, even if the moment is about the very point that I'm summing moments, it still goes in the equation if I'm writing the moment equation. It's just, is it plus or is it minus? This one's plus. I've got ML, so plus ML. Concentrated moments don't have a moment arm, so I don't multiply by delta X over 2 or anything like that. I just plus ML. Minus, now here I am interested in changing moment, so I'm going to use the ML plus delta M version. So minus, because it's going counterclockwise, ML plus delta M. And then the point load does not create a moment about C, but the distributed load could. So there's a lot of ways we could handle this. What I'm going to do to handle the distributed load is I'm going to say that there's some coefficient, A, because it doesn't have to be an evenly distributed load. It's just some kind of coefficient, and there's I don't know what the value of it is, but there's some factor A times the lumped version of the distributed load, which is well, let's just call it times W. Do I need to do that? Well, W times delta X, because that's the magnitude of it. So we don't know what A is. We just know there's something. You have to multiply W times delta X, the lumped version. You have to multiply it times its moment arm. So it would be like this. If I had drawn an unevenly distributed thing, then maybe the lumped version is over here, and A would be that distance, right? I don't know what it is, but there's some number I have to multiply by, and the lumped version is W times delta X. Not, let me write times, not parentheses. And W itself could be some function of X. So I have to figure out the area under the curve, and I have to multiply it times some moment arm. That's what I have to do. I just don't know what any of that is. So I'm just going to kind of generalize it as some number A times the lumped load. That's what I'm going to call it. And I don't even know if it's positive or negative. I'll let whatever A equals take care of positive or negative. Don't worry too much about it. We're going to get rid of it anyway. All right, let's see what we can do here. First of all, I see I've got ML minus ML, so those subtract each other away. Then I've got this thing, right? So what this is the shear force on the left-hand side times delta x over 2 plus the shear force on the right-hand side times delta x over 2. I could rewrite that a little bit as I could collect them on delta x over 2, right? So VL plus VR, well, let's do it that way, times delta x over 2. I could kind of rearrange it a little bit and write it this way. VL plus VR, well, let's write it the same way, over 2 times delta x, and VL plus VR over 2. So I've got a number on the left-hand side, I've got a number on the right-hand side, I add them together and divide by 2. So whenever I have one number and I add it to another number and I divide by 2, all I've done is I've averaged the numbers. So I'm just going to say that that's V, technically it's V average, but I'll just say V times delta x. Okay, that's what I'm going to do for that. Plus C, I've subtracted that ML minus ML, so they aren't there. Minus delta M, and then I've still got this plus whatever A is times W times delta x. All of that equals 0. I don't like the negative delta M, so I'm going to move it to the other side so it's positive, and I'll end up with this equation. Delta M equals whatever V is times delta x plus C plus whatever A is times W times delta x. That's going to be my generic form of this equation that describes the bending moment, internal bending moment. All right, so let's do a similar to this approach where we write some, well, what if this is true, then that happens. So if, then. So first, let's just say that C is 0, so there's no concentrated moment. That's generally true. And then these other two things, the distributed load and the shear force, are equal to, or they're not equal to, they're multiplied times delta x. So I can, let's see, I'm trying to think of the best way to say this. So as delta x goes to 0, all right, this is not quite the same as what we had here. Oh, well, no, what we had here, right? So I have two things multiplied by delta x, right? But one of them is multiplied times a, and a is some fraction of delta x, right? Because a has to be some tiny part of delta x. So the 1 times a is going to go to 0 faster because it's some number less than delta x times w. So it's going to go faster to 0. So what's going to happen is I'll have delta m equal to v times delta x, and the one with the a in it has already gotten to 0, so it's zeroed out. So what this looks like is I'm going to rearrange again. Delta m over delta x equals v. So the delta m over delta x is the same as it was before when I had here. I had delta v over delta x instead of the slope of the shear diagram. This number is describing the slope of the bending moment diagram. Nope, not there. Here, let's see. So here, the blue line on this picture is our slope of the, or it is the bending moment diagram. And so anywhere on it would be the slope. Any tangent line to it at any point is the slope. So here's one that's easy. The slope here looks like it's horizontal from this 3000 dot over to here. It's horizontal. That would mean the slope of 0. But if you look at the shear diagram, there's 0 shear. It's on the x-axis where it equals 0. So the 0 shear, 0 slope. Here, from the very left-hand corner up to this 2000 dot, that angle, we don't really know what that angle is, but the slope of it is right here. It's 200 newtons per meter, because the slope of this is equal to the value of the shear. Now here, this one's different. The shear is constantly changing, but you can't quite tell on this one. You can tell better on the next section. But this is actually curved. It is jagged, yes, but it's not straight because it is a curve slope. Because the shear is changing, that means the slope is changing. Here at this point, it looks like the slope is 0, so there's kind of a horizontal point of inflection right there. So you can look at the value of the shear diagram, and that will tell you the slope of the moment diagram. Also, look at this, the area here, this number 2000 is the area to a height of 200, a width of 10 meters, so technically this is 202, oh well, so I'm going to say that again, height of 200 newtons, a distance of 10 meters, the area here is 2000 newton meters, 200 newtons times 10 meters. This total change from where I was, which was 0 when I started, up to the dotted line here, which signifies the end of this region, which also corresponds with the beginning of the distributed load. That total change is 2000. It's the total change is equal to the area under the curve. In fact, if we went over here and let's do this, delta m over delta x will integrate both sides with respect to x, and you get m equals the area under v. So that's why when they were drawing their shear diagram, these numbers here, whoops, the 2000, the 1500, the 500, those are the areas of those regions because they're integrating the area under the shear curve so that they can figure out how much change there is, not the value, but the change of it. Look at the next one. They said that the area here under this part of the curve is 1500 newton meters. And then they started this region, this kind of peachy colored one. They started it at 2,000. They went up because all of these shear forces are positive. They're above the x-axis here. They went up 1,500, so they were at 2,000. They went up to 3,500, but they didn't take like a straight line route. The shear is not constant here, so the slope is not constant here. And so what we'll talk about, well, how do you know which way to curve the bending moment diagram in a second. But they did go generally upwards, but it does kind of taper off towards the end. And if you think about it, there are larger shear values here, smaller shear values at the end of this distributed load. This isn't the end of the distributed load. It's just interrupted by this point load. So it's kind of the end of this little segment of the distributed load. And so I have a higher slope here, and a slope that gets closer and closer to zero here because the magnitude of the shear has decreased. So the value of the slope has decreased. We'll work through some of those. All right. So what if C is not zero? This is not common, but because there aren't that many times on a free body diagram of a beam that there's a external concentrated moment, but it can happen. This beam had one. Look, there's one right there. There's an external curved arrow, 3,000 Newton meters. So if C is not zero, there's some value. Then my equation gets dominated by C, right? So as delta x approaches zero, then the V delta x and the AW delta x, they both go to zero, and C is left as the dominant feature there. This is the same idea as the single point underneath a point load. So delta M equals C. So what that says is that there is a step change in the bending moment diagram and that step change is equal to C. So in our example we've been looking at here, right here where there's the external 3,000 Newton meter concentrated moment, we were at 3,000 right here at this orange dot. We immediately drop down. Now we go down because this is counterclockwise. So this is one thing I've been saying several times. Every time I draw these, these little forces, I say there's a sign convention that we have to follow. So what our sign convention is going to say is that external bending moment so a clockwise one is positive and a counterclockwise is negative. So we just have to agree on that. It's for all of our stuff to work out. It also means whenever we follow all of this convention that clockwise bending moments produce a tension on the bottom, and therefore compression on the top, and a counterclockwise, which is going to be negative, produce tension on the top fibers of the beam. So how you remember that is, so tension on the bottom fibers, is this kind of shape. I've got tension here and compression here, and tension on the top would mean it's bending this way. So got tension on the top, compression on the bottom of the beam, because remember when a beam flexes, every section has both tension and compression on it, and zero. The neutral axis has zero stress. So positive moments do this, and negative moments do this. And it's really easy to remember. I don't think I've ever forgotten that. How do I know if it's external? Oh, so the internal ones are the ones that when you cut the beam open, that's the internal one. Anything on a, let's go back to this one. Anything that's drawn on a free body diagram like this, you know, this beam is not cut open. It's just the whole beam. That's an external one. So, and these that you're drawing pictures of, this shear and this moment here, these are internal. But anything on the free body diagram that if the beam has not been cut open is external. So this would be something like, I don't know, what would be an easy way to, so maybe let's draw some kind of, let's draw this. So here's your beam, and it's a T-beam, so it's got a T shape to it, but you've connected another beam to it somehow. So let's say that you have connected a beam here, some kind of rod or whatever, and you know, you've riveted or whatever, and you put a point load up here. Then it's some distance away from the beam. Oh, that was very, very raggedy. D and F. Then when you were actually analyzing this thing, what you would do is, instead of all of this stuff, you would put a concentrated moment to replace the effect of having this thing bolted onto the beam with a force at the end of the thing, whatever this little rod is. So there are ways that you might, this concentrated external moment is representing something like that. You know, is it that exact scenario every time? No, but it's something like that. I was going to move this and it didn't want to move on me. There. So that's how you might get an external concentrated moment. But so you might only start with, you know, this version of it. You never saw, as a problem statement anyway, you never saw this version, but you saw this version. And that curved arrow, if this is not like a free body diagram like this, where we've cut it open somewhere, then what you're looking at is an external concentrated moment. All right, so this little thing makes it easy to remember. Oops, I didn't want the force. This little guy makes it easy to remember that positive moments give you the smiley face, negative moments give you the frowny face, and that'll tell you where the tension is on the bottom or the top of the beam when you draw out the smiley face version. All right, we have enough rules now to actually do one of these things. We don't have many rules for the concentrated moment, because either there is a concentrated moment or there's not one. And if there's not one, then basically whatever's going on in the shear diagram is controlling what's going on in the moment diagram. So for the most part, the moment diagram is just the integration of the shear diagram for the most part, and it's interrupted every now and then if you have a concentrated external bending moment. All right, let's find one that we can work on. Let's see. That one's relatively simple, but we can do that one. I think we actually did this one. This might be one of the ones that we did some of the other version on. But let's use this one and draw a shear and bending diagram of it. So I'm going to get this. Actually, I'm going to cut the dimensions off and plug in whatever. Well, I'll just draw over it. All right. So let's get us a new area. Let's make it a little bit bigger. Maybe like that. Can I make it just longer? Well, it kind of stretches out. All right. And we'll just make up some numbers for all these dimensions. Let's say that F is equal to, I don't know, let's do 5 kips. Remember, a kip is 1,000 pounds, so this is 5,000 pounds. W, we'll say that that's equal to 1.2 kips per foot. So 1,200 pounds per foot. A will be, I don't know, 4 feet. B looks like 3 feet. And C looks like 1, 2, 3, 4, 5, 6, 7, maybe 8 feet. Something like that. All right. So the first thing we have to do when we're drawing a shear and bending diagram is we have to know the reactions at the supports. So I've got supports at A and D, a pin and a roller. So I've got to find those values. So what I normally do is, normally I would draw the free body diagram of this thing, but I'm just going to assume that you know there's 2 reactions at A, and AX and AY. AX is 0 in this case. And at D, there is a roller. So there's 1 reaction, and it's perpendicular to the surface the roller is on. That's a horizontal surface, so it's a vertical dy. If I were to draw them, I'm not going to leave these on here, but if I were to draw them, I'd have AY and AX, and I'd have dy here. I don't like drawing them on top of the diagram because it makes it kind of look like, or at least you're unsure if there's a dy and the reaction from the roller, but there's not. Dy is the reaction from the roller. That's why I don't like just drawing them on top of the picture. So I'm going to erase them. And just remember that that's what I'm talking about for AX, AY, and dy. All right. So summation of moments about the pin is what I normally do. And the pin is labeled A in this case. So I've got my 5 kips times a moment arm of 4 feet. I'm going to have to, there we go. I've got my distributed load. Now this one I will draw on top. The lumped version of my distributed load. So the lumped version is 1.2 kips per foot times 8 feet. So it's a total of 9.6 kip. And then this distance is 4 feet. Okay. So I've got 9.6 plus 9.6 kips with a moment arm of 4 plus 3 plus 4 is 11 feet. And then I've got dy, which I'm assuming is pointing upwards, so minus dy times its moment arm of 8 plus 4 plus 3 is 15 feet. The only unknown in that equation is dy, so dy equals 5 times 4 plus 9.6 times 11 divided by 15. 27.04. So one thing about these shear and bending diagrams is that if you round a lot, so I calculated 27.04, right? And that would be kips. Actually, that seems a lot. Maybe I did something. Oh, I did. Let me check and make sure that that's correct. I've got 5. That doesn't seem right. Hold up. 5 times 4 plus 9.6 times 11 divided by 15. All right, 5.7. All right, I don't know what I did. I did something wrong. So 5.7, but it comes out 5.70 and a bunch of 6s. So I'm going to round it somewhere, maybe here. So what'll happen is when I'm drawing my shear and bending diagrams, the ideal situation, let's see if I can find the one we were looking at. Sure, here. The ideal situation is you start at 0, you do all your rule following, and you end at 0. On both the shear and the bending moment, they both start and end at 0. If you do some rounding here like I did, then that may not happen. You may not end exactly at 0. As long as you're within some kind of minimal amount of tolerance, then that's probably fine. It just means you rounded. But if you're off by a lot, then you probably did something wrong. So you might want to go and check all your work again. So I probably will be off a little bit in the moment diagram just because I'm rounding here. And then summation of forces in the y direction. I'm assuming y is positive if it goes upwards. So I've got AY. I've got minus 5, minus 9.6, plus dy, which we just found to be that number. I'm assuming dy points upwards, equals 0. So therefore AY is equal to, let me see, 8.89. Also pointing upwards. So you'd be slightly better off if you drew the free body diagram of the beam with the arrows for AY and DY. I just didn't want to redraw it. Now, you have to, this is why I draw the lumped versions in a different color, is so that I can ignore them, because now I don't want this 9.6 lumped load as part of my shear and bending diagram. It was only there to help me calculate the reactions. So what I'm going to do is I'm going to drop lines from every one of these points here. And these will help me align my shear and bending diagrams correctly. Now this one does not have a concentrated moment on it, so this one won't give us all of the details that we might end up with. Maybe we'll work another one, depends. Now I'm going to draw a horizontal line for where V equals 0. I wrote all my forces in kips, so this is going to be kips for units. And then maybe I should draw the AY and DY on here. So just know that these are not additional forces to the reactions. These are the reactions. So AY was 8.89 and DY was 5.71. Okay. So how you do one of these, 8.37, that's possible. Let me see. Let's see, 5 plus 9.6 minus 5.71. I still get 8.37. Huh. For dy. Alright, so let me see. 5, I could have put something in wrong. 5 times 4, is that right? Yes. Plus 9.6 times 11. 4 plus 3 is 7 plus 4 is 11. I wonder if I've got an order of operations problem. Oh no, I did get that. Alright, so alright. Ignore all of those numbers. Do the process, but calculate it correctly. That's also going to change this value. Thanks for getting that fixed up. 5 plus 9.6 minus 8.37. So this one is 6.23. So what would have happened? This is one good thing about the shear and bending diagrams, is that we would have drawn the shear diagram and it would have worked out, start at 0 and end close to 0. But when we drew the moment diagram, it would not get close to 0. And it would be because I had the wrong values for AY and DY. And so that would give us it couldn't resolve correctly, and you would know that something somewhere was wrong. It might have taken you a while to trace it all the way back to your reactions, but that's possible. I'm just recalculating. All right, so that seems right. All right, so AY apparently 6.23, DY 8.37. Okay, those are kips. And all right, I'm not seeing any other issues in the chat, so hopefully we're on board now. All right, so you start at 0. And in this case, immediately, like right at the 0, x equals 0 point, there's a reaction in A. Now, technically, you know, there's this little section of the beam that in my picture is not, you know, not at 0. It's in the, it's on the left side of the y-axis. We're ignoring stuff like that, so don't worry with that. So point load, that's this scenario. P does not equal 0. Change in shear equals P. That's this scenario. All right, so I'm at 0 because I started at 0. There is a point load of 6.3 kips, so I'm going to immediately go up 6.3 kips. Now, I didn't put in scale on here, but let's do 2, 4, 6. We'll call that 6 right there, and so 6.3 is something like right there. So it goes straight up to that line, and then you usually want to put, you know, the value over there. And then nothing happens until I get to point B. So when there's no point load, you know, when there's no point load, no distributed load, then the change in shear is 0. So it just stays constant. So that means it just goes straight across here. Then, all right, so I'm at 6.23 in my shear. I encounter a point load pointing down, so it's negative, of 5 kips. So 6.23 minus 5 is 1.23. So it goes down to somewhere like that. And again, there's no change until I get to point C. So it just goes straight across. Then I get to a distributed load. This is, ignore the purple lumped load, just the distributed load. This one, I'm at 1.23. I'm going to lose, because the distributed load is pointing down, I'm going to lose 1.2 kips per foot over a span of 8 feet. So I'm at in my calculator. Whoa, drop my calculator. Let me redo my calculator. 1.23. So in my calculator, I put in 1.23. You can't see, it's all blurry. Minus the total amount here. So 1.2 times 8. And I go down, and conveniently, I go down to 8.37, negative 8.37. 1.23 minus the quantity 1.2 times 8 is equal to negative 8.37. So if I were doing the same scale, this would be 2, 4, 6, 8. I'd be down at, you know, somewhere there. And it's a straight line like that. And that point is negative 8.37. And then as soon as I get there, I encounter dy, which is a positive, it's pointing upward, 8.37, so I get all the way back to 0. Okay, and so that is the shape of the shear diagram for this particular beam. And what it tells me is that if the beam fails in shear, the most likely place is right at the roller. That's where I've got the largest shear force. Now it's negative, but shear doesn't care if it's positive or negative, so that would be my most likely case. Now it probably is not enough shear force to actually make the beam fail, but if I were considering failing in shear, that's where I'd look. Now, remember over here, well, not that one, but the other one we were looking at, this one, they put all of these numbers in the area. We need to do that. So basically that is integrating our shear diagram. So the first one's easy. It has a height of 6.23. and a base of 4 feet. So this first number is, I'll write them in green just to keep them separate. 24.92. Those units would be kip feet. I usually don't write the units on these because it's it's too cluttery. And that's just for that first rectangle. So just for this. Okay. The next one is also a rectangle. It has a height of 1.23 and a base of 3 feet. So 3.69 I'll try and squeeze in there. I'll draw it with arrows going a different, or hatches going a different direction. Okay, that's a 3.69 if you can't tell on there. Now it gets interesting because I've got this triangle thing from the distributed load, but it's two different triangles. So I've got one that is just this little guy. So the area of that is the base times the height divided by 2 because it's a triangle. The problem is I don't know this distance. I don't know that. So I have to figure out what is x. So how I do this is it goes back to, remember here, the slope of the line that represents the shear under a distributed load is equal to the value of the distributed load. So this slope is equal to 1.2 negative, because it's going downwards, negative 1.2 kips per foot. So basically what I have to figure out is I'm at a height of 1.23 kips. How many feet does it take me to get to 0 if my rate is negative 1.2 kips per foot? So I just divide. And it's 1.025. So if I write the equation out, 1.23 kips divided by 1.2 kip per foot equals 1.025 feet. So x is 1.025 feet. So the area here is, I don't have room to write it in that little spot, is the height, 1.23, times the base, 1.025. Don't forget to divide by 2 because it's a triangle. So it's not much, but it's 0.63. I'll leave it there. Kip feet. And then the last one, if the base of the little green triangle was 1.025 feet, the base of the big triangle is 8 minus 1.025, so 6. So this distance is 6.975 feet times the height of negative 8.37. Don't forget to divide by 2. 29.19. But it's negative. And that would be for this triangle. You do not have to shade them in. I'm just trying to make it as clear as possible on what is what. Alright, I don't see any new fixes in the comments, so that's good. Alright, so we have integrated our shear diagram, and it's time to draw the moment diagram. So I'm going to scroll down here. I'm going to put a line for the moment diagram. I'm going to say m equals 0. The units on this are going to be kip feet. Now I'm going to add a line here. So I'm going to add, maybe I'll do a green one. I'm going to add this as kind of a reference for where that thing crosses 0 at. So something like that. Kind of got cluttery there. Where I normally don't write out that equation, but we did in this case. We'll draw, these can be red. Alright, we're going to start at 0. This one has no concentrated moment, right? The original beam had no concentrated moment, so we never get to this part. So there's never a step change in our moment diagram. What that means is that the M, oh, this should have been delta M, huh? The change in moment is equal to the area under the V. So I left off the delta on that M right there. So I just figured out for the first segment here from point A to B, that's one block in my shear diagram. The area is 24.92. It's positive, meaning that the shear is all positive shear. So 0 plus 24.92 is 24.92. I kind of need to know what my scale is going to be. Let's see. I kind of want to be 25. Let's count by fives. So 5, 10, 15, 20, 25. There'll be 30. So I'm going to go from 0, where I start, up to, oh, wait, hold on. Can you explain the step for the one? Oh, okay. Yes, let's do that first, and then we'll do our moment diagram. So the question is about this, The question is about this part. So assuming that we're okay with getting the red line, the diagonal red line, then that's a different thing, but that's coming from the fact that we have a distributed load. And the distributed loads they don't always, but they can force the shear diagram to go from a positive number to a negative number. So it crosses 0, it crosses 0 right there. I don't know if you can see that. That's kind of hard to see, huh? It crosses 0 right there. And so what that'll do is it'll break that triangle into two separate triangles. They may be equal. In this case, they're not even close to equal. But I need to integrate both of them. So I need the area of each of those triangles. And so the area of the little solid green triangle is, let's put it over here. So this is a giant version of the little green triangle. We know the height of our triangle because it's given to us in our shear diagram. This height, actually let me draw it as a height. I usually use blue for that. So this height is given as 1.23. Technically the units are kips. But this base is not given to us in any way. Now, you could try and, like, if you did a very accurate drawing, you could try and measure it or something like that. But that's not a good idea. So we're going to have to calculate that. Now, the other thing we know about this triangle is that the slope of this line, so in our diagram it's actually a red line, the slope of that line is directly related to the value of our distributed load. So the slope of that line is actually, and it's pointing down, so it's negative is technically the slope, 1.2 kips per foot. And that came like directly from the value of the distributed load, and the distributed load is what created this triangle in the first place. Okay, so if I know that the slope of the angle, the hypotenuse of this triangle is 1.2 kips per foot, and the height up here, this little peak up here is 1.23 kips, then how long at that rate, negative 1.2 kips per foot, does it take for me to get from 1.23, where I'm at with this red dot, down to here, which this is 0. So that point's 1.23 kips, and this is 0 kips. That's where it crosses the shear equals 0 line. So all I have to do is divide those two numbers. Divide 1.23, the current height, by the rate that I'm losing height, 1.2 kips per foot, and I will find out the distance x. So x is just equal to 1.23 kips, the height, divided by the rate, and I'm dropping the negative sign on here, because I know it's not a negative distance. And that gives me the 1.025 feet of x. So basically, it's how many feet under this distributed load will it take me to get from wherever I started at, 1.23, down to 0. And these are a little bit confusing because they're similar numbers. 1.23 is the height, and 1.2 kips per foot is the rate. But normally that's just coincidence that they're similar. Normally they're very different numbers. So you just take the 1.23 divided by the 1.2, and that's how long, how far does it take you to get to 0. Hopefully that makes sense. If it doesn't make sense, all you have to know is take the height of the triangle and divide by the rate of the distributed load, and that will give you x. So that's what will happen. And then maybe as you do these and you get to see some other triangle options with different numbers, they'll start to click on what's going on. All right, now back to our moment diagram. Like I said, you always start at 0. Sometimes immediately something happens. So for a moment diagram, you could have a external concentrated moment right at this point, and it would immediately go up or down. That happens with cantilever beams. We haven't done a cantilever beam, but that would happen with one of those for sure. All right, so the rule when there is not a external concentrated moment is that the change in shear is just equal to the area under the curve, and the slope of the shear, the change in the moment, let me say that again, the change in the moment diagram is equal to the area under the shear diagram, and the slope of the moment diagram is equal to shear. So it's sort of acting like the distributed load. So the area is a positive 24.92. I'm at 0, so 0 plus 24.92 is equal to 24.92, so there somewhere. In this region, I have a constant shear, so I have a constant slope, which is a straight line. And I just connect the dots. So now I'm at 24.92. Okay. Now for the next section, I've got another little rectangle in my shear diagram, and I'm adding 3.69 kip feet. It would be the units. So I'm at 24.92. So I just keep these in my calculator, and then I add or subtract as it tells me to do. So 24.92, I've got a positive shear, so plus 3.69, I go up to 28.61. So that's going to be maybe, that's 30, so maybe it's like right there. 28.61. I have a constant shear in this region, so I have a constant slope. So something like that. And then I've got the little solid green triangle. It's positive, so I add on another 0.63, so plus 0.63. So I'm up to 29.24. So like right under the 30 number, 29.24, and it is a shear that's not constant. It goes from one number down to 0. So in this little span here, it's not even going to be noticeable, but technically this one curves. So you can't even see it, but it curves. And then look at this. I'm at 29.24 positive, and then the last triangle is a negative 29.19. So if I round both of those to one decimal, they're both 29.2. And so I get down to 0. Now this one starts at 0, which is a horizontal slope, and then it gets more and more negative. So that means the slope gets more and more negatively steep. So something like that. Is that the exact shape? No, but that's the general idea of what's happening. And I got more or less to 0 because I was at 29.24 and I subtracted off negative 29.19. That's what I was talking about. Sometimes, depending on how you round, the moment diagram may not come out exactly at 0. So anyway, what this tells me is that my maximum internal bending moment, which is the whole, well, a large point of what we're trying to do here, M max equals 29.24. Those units would be kip feet, and it would be at, that would be 4 plus 3 plus 1.025. Let me add all that. 4 plus 3 plus 1.025. 8.025 feet from the left end. However you want to do that. You know, however you want to say that it's from the left end. So now I know the value of the maximum bending moment, and I know the location. So now I can go in and figure out where the worst case scenario is, and what the, you know, is the beam likely to fail under that load or not. Depends on what kind of beam it is. But before, just looking at this thing, I probably could guess that the maximum is somewhere near the center, but other than that, I wouldn't know exactly where, and I wouldn't know its value. So that's kind of the point of these shear and bending diagrams. Let's see. So the area, I'll just, we'll draw it yellow, I guess. Whoa, didn't want to do that. There we go. So all of this is the area under the bending moment diagram. And normally you're looking for the maximum one, which is what we found at 29.24 being the maximum. Sometimes you're just trying to draw the shear and bending diagram. Now, on an exam, you can't really draw on an exam very well, on these exams anyway. So what you have to do is, normally I'll give you a beam like this one, and I will give you 5 or 6 options for what the shear or what the bending moment might look like, and you have to select the right one. Okay, how did you get the 28.61 number? 28. All right, so 28.61 is 24.92. So that was, I was at this point at 24.92, which is basically, you know, that number. And then 28.61 is equal to the number I was at, 24.92, plus the next little segment, 3.69. Getting arrows everywhere. So all that happened in that segment, if I go back to my rules, C equals 0, there's no concentrated moment there, then the change in the bending moment is equal to the area under the shear diagram. So the area under that corresponding shear diagram was 3.69 kip feet. And so the change in shear from where I was, 24.92, plus the change, 3.69, equals the new point of 28.61. So each time I'm adding or subtracting the area under the shear diagram for that little region. I add it if the shear is positive above 0, and I subtract it if the shear is negative below the 0 axis. That's also why I put the negative sign on the one that's negative, the one area that's negative. You don't always just have one area that's negative, but that's kind of common. Okay. I don't think we have time to do another one. But we will do others, because this is kind of going to be the starting point. We're going to now use these combined with our flexural stress equation. We're going to actually do what we might call design beams, although a better way would be select beams, select the appropriate beam. We'll do some more flexural stress calculations, but we're getting close now, getting close to the exam 2. So where did I put exam 2? There it is, July 25th. So actually we've got a ways to go on exam 2 still. Oh yeah, because we're going to do beam deflection also. So not only do we want to know the stresses in the beams, but sometimes a beam fails just because it bent too much, and so we're going to do that also. Speaking of exams, exam 1, I've gone back and I've graded. So you know it gives you an automatic grade. I've graded about 1/3 of them, so I'll finish up the other 2/3 soon. They're not in any particular order. You'd think they'd be alphabetical or whatever, but Canvas just has them in there in, I don't know, some order. Maybe it's first name alphabetical, I don't know. But for whatever reason, they're just kind of scattered around. So you might have seen your exam 1 grade change. If so, that means I've done yours. Otherwise, I haven't gotten to it yet. So I've only done about 1/3 of them. All right, I've opened up some web work. You should see, let's see if we go to the homework sets. Well, I've already been logged out. You should see homework 13 is open now. 12 and 10 are still open. The optional and the special 2s are open if you want to work on those. No reason to do the optional 2 yet. I would use those to study for the exam. But the special 2, those are the ones that you can get some extra credit for. Oh, the exam grades. So I'm not sure what it shows you, if it shows you the score or your percent. So you want to look at the score. So maybe I can view it as a student somehow. I don't know, but the score is out of 106, but the percent, it takes and it divides what you scored divided by 106 and gives you that percent. So the actual grade that I'm using for calculating your final grades is the score. So technically you could get over 100 on this exam. There was bonus points. There were bonus points. So I don't think I've seen anyone do that yet, but I have only done 11 of them. So if it shows you a percent, then no, you actually might have, well, you would have a higher score. And I just don't know if it shows you the score or not. So the number out of 106, just drop the 106 and that's your grade, versus the dividing your number by 106 to get a percent, if that makes any sense. If there are groups, how many people? So for the group project, we haven't really gotten to the group project yet, but I typically do up to 4. So it's kind of, sometimes it's hard to find the groups, so you can go down to 2 if you wanted to. And then sometimes, but not never, there are people who are so remote that they're in another country somewhere and they have to do the project on their own, which is fine. But up to 4 is what we're looking. That's a decent sized group for this. The moment diagram is just treating the area of the V as a slope. The magnitude of the V. So the area of the V, like this 24.92, is the change in moment diagram. So the slope of this red line for the moment diagram is the magnitude of the thing. So for instance, of the shear. So for instance, this first section from A to B, here's A, B, C, D. The slope of this line, if we did a run of 1, the slope would be 6.23, which is coming from right here. So the slope of it is related to the magnitude of the shear. And notice, look at the first section, A to B, I've got a steep kind of slope. And then the second one, if this is 1 unit, that rise is, well, I don't have room to write everything, 1.23. And it's a much shallower slope because there's less shear there. So if you're thinking of the slope, oh, it didn't switch screens. I'm drawing and it did switch. I was still, let's see, there you go. So what I drew on here was was this part right here, the slope in section A to B. related to the rise of that slope is the magnitude of the shear. The run is just 1, rise over run, and I just unitized it to 1. And then the section from B to C, right here, the rise is only 1.23, because I have much less shear in that one, so it's not changing the moment as much as the section from A to B with the larger shear value. And then the ones that have the changing shear, the ones that are at the shear is at an angle, like the triangles, then those have curves in the moment diagram. Next time we'll talk about how to, figure out what way to make the curve. All right. Let's see. Question about, is the exam 1 time apart? No, exam 1 time. If you were going to take it at noon versus 7, you could fill that out. It didn't really matter this time. I used that in the past because I had to print papers and bring them to different times, but here you don't have to do that. So it didn't matter. You'll get a 0 out of 10, but it's not a grade. Not a graded item. All right, so I think we're good enough for now. Obviously, your web work, you can't draw these diagrams, so there is there's a way to basically input all the vertices. You'll see when you try to do some of these shear and bending diagrams in web work, it's a little tedious. I would still draw them out and then translate that into the way WebWork wants it, and hopefully it makes sense on how to do that. If it doesn't, we can do one, or at least part of one, in one of the streams. So exam 1, so I don't know how it shows your score. So let's just say, let me give you some numbers. Where's my calculator? We are on the right screen. I just need my calculator. I don't know what I did with it. Here it is. All right. So let's say on exam 1, you scored a 75 out of 106. Like, that's your score. I had 106 points available on exam 1. Then the grade that I'm actually going to use to calculate, when I go to calculate your final grade, is 75. But what it might be showing you is 75 divided by 106. It might be showing you 70.8%. So Canvas might be showing you that. But your actual grade would be a 75. So I don't know a way in Canvas. I haven't gotten familiar enough to figure out how to do bonus points on an exam. Maybe there's a way to do that. So if it's showing you a percent, that's actually lower than your actual grade. Your grade is how many did you score out of 106, but don't divide by 106. Just take that number, 75, in my example here. Hopefully that makes sense. I just don't know. I don't know how Canvas is showing you your grades is the problem. If I see a number out of 106, just take that number. So if you're saying that Canvas shows you some number out of 106, that number is your grade. Don't divide by 106 to get a percent. Alrighty. We will be back Wednesday, and should be graded, or regraded everything by then, I would think, if yours hasn't gotten already done. It doesn't take terribly long. I just haven't gotten the last 2/3 yet. All right. I'll be back on Wednesday at noon.